This is topic 4.6, approximating with local linearity. We're going to begin by talking about the tangent line of a function, let's say at x equal to a. So let's see if we can get maybe like this, and here's x equal to a, and we're talking about the tangent line there at x equal to a. Okay, so now if we have that tangent line, what we can do is we can approximate function values for x values close to a. So let's just say we want the y value here at that x value. We could use this tangent line and we could say that is the approximation of the y value. Now we do know from this graph that it's really here. But if we don't have the graph, we can then just have the tangent line approximate those values. Now, when you really think about this, we're talking about values that are really close to a, like right here. So it would literally be right there. And so approximation is right there. So we're really a lot closer than what my diagram shows. But that's really what we do. Now, let's talk about concavity. This is concave up. And it might help you remember up has the U in it. And so it is a cupping upwards. Okay? Now, any tangent line approximation to a curve that is concave up is an underestimate. Okay? Why is it an underestimate? In my exaggerated example, this is the actual y value there. And this is the estimate. And if you can see, it is less than. So we have an underestimate of the actual value from my linear approximation. Okay, let's go to concave down. Let's say we have, and let's say we have x equal to a here. And we'll go ahead and have our tangent line. Let's see if I can get it pretty good right there. And then have our line come through here like that. Okay, so that is the tangent line at x equal to a. And let's just say we have a point really close to a. I can go to the right again. Whoops. I can go to the right again of a, right about here. Now we're really supposed to be much closer. So that y value, we would approximate it with this line would be there. Now the actual is actually here. So this is the actual and this is the estimate. So you can see that we have an overestimate this time. So if you approximate the value on a curve that is concave down using linear approximation, you will have an overestimate always. And if you think about it, look, here's the tangent line there. There, it's there. So all of these lines will approximate values that are much greater. Okay? And one thing we know how to do in calculus is write equations of lines. So I think after this, you're going to be very relieved, and I think you will be just fine. Okay? So let's go ahead and take a look at number 1 here. And so we're talking about a function that is concave up. And you know, it may be that right after you see that, right after you see concave up, you actually draw a curve that is concave up. I'm going to draw it down here because can we already answer this question if our function is concave up and we're going to estimate a value using linear approximation? Do we even have to look at A yet? No, right away we know that any tangent line is going to be below, and all of these approximations that come off of that line is an underestimate. So we do need to justify. So you would say underestimate since f of x is concave up. So you will need to justify, okay? Or you could say because. Okay, now let's go to actually writing the estimate. We sure jumped the gun there. We went right to B because we know that it's going to be an underestimate if it's concave up. And it's something you don't have to memorize. Just draw a concave up curve and draw a tangent line to it. If it's below, it's an underestimate. So it's not too difficult. Okay, so what we want to do is we want to, and I think there's... yeah, they give us all the information. F is concave up on its domain, and f of 4 equals 5. So we have a point. And f prime of 4 is 3. So that slope is 3. Now, they want us to first write the equation of the tangent line. Then we're going to use the tangent line as our linear approximation line. So that line is what we will approximate values for. Now, we are creating the line at x equal to 4. This is really important. The line is created, the tangent line is created for the tangent line at x equal to 4. So we will be approximating x values close to 4. Look at 3.8. 3.8 is very close to 4. Now, this would not be a good line here that we're going to draw to approximate the value on the function, that we don't even know what it is, for x equal to 7.5. We would want to first find the tangent line a little bit closer to 7.5 and then use that line. Okay, so let's go ahead and write this line. We're pretty good at this. Y minus the y value equals the slope x minus the x value. Now, can you go ahead and solve for y? Absolutely. Y equals 3x, and that's minus 12 and a plus 5 minus 7. But I'm going to tell you something. This is sometimes a nicer version because no one said what's the line. We just need to write the line in order to use it. So what is our x now? Our x, we want to find f of 3.8. We want to approximate f of 3.8, okay? Now, 3.8 is on the graph, but we're using the line at x equal to 4 to approximate it. So look how this first equation is much nicer. Well, we would just use 3, since you're going to have a calculator, 3 times 3.8 minus 7. So that's equal to 4.4. Now, what I was trying to tell you is you can see that if you put 3.8 in here, you get a negative 0.2, and it's much easier to do without a calculator. But so sometimes it's easier to not solve for slope-intercept, but I ended up doing it anyway. Okay, so that wasn't too bad. Let's go ahead and look at number 2 and see what we have. So here we have a function, f of x equals 5x minus 2x cubed minus 2, and they're telling us that it's concave down at x equal to 1, okay? So before we do anything, if I have a concave down function, and let's just say this is my tangent line, you can already see this is going to be an overestimate since f of x is concave down. Okay? We've already answered C. We weren't even starting yet, okay? So, and then let me show you on this graph what we're actually going to be doing. This estimate we just found was at x equal to what we're going to find is at x equal to 1, okay? But we're going to be approximating f of 1.1, so right next to it, we're going to get this y value. The true y value is right there, okay? So we already can see we're going to have an overestimate. I hope that makes sense. Okay, so now we're going to first start with the tangent line. So everything we have done before, but it is going to be our linear approximation, the line we use for our linear approximation. So what do you notice? I've got an x value. I don't have a y value. I need a slope. So I have a little work to do. So the first thing we want to do is find that y value. So how do I find that y value? Y is going to be f of 1. And that's going to be 5 minus 2 minus 2. And so I got a y value, looks like 1. 5 minus 4 is 1. So now I can put that 1 there. So all I really have to do is get the slope. Well, the slope in calculus is just the derivative. So the slope is f prime of x, and that's 5 minus 6x squared. And now f prime of 1, and we get 5 minus 6, and that's a negative 1. So now we can just write the equation of our line. Y minus the y value equals the slope, x minus the x value. We can leave it like that. Let's do that this time, since on the previous problem I solved for y, and you'll be able to see why sometimes it's better to leave it in that form. So this is now, not only is this our tangent line at x equal to 1, it's also going to be it's going to be our linear approximation for any values close to 1. Now, 1.1 is pretty close to 1, so we can use that line to approximate the value on the graph. Okay, so what do we have to do now? We have to just take y minus 1 equals negative 1, 1.1 minus 1. So we have y minus 1 equals negative 0.1. So if you do the math, you just have to add 1 to that, and you get y equal to 0.9. So what you can say is f of 1.1 is about equal to 0.9. Okay? And you could actually plug 1.1 into f of x. You could try that, what the actual value is, and see how close you are. Okay? Okay. Let's look at number 3. Now, I don't want number 3 to bother you. We are going to just immerse you in this. They're giving us a differential equation. Why is it called a differential equation? Because it's an equation with a derivative in it. That's all it is. This equation has a derivative in it. And we've been doing that with implicit differentiation and just taking the derivative. We have dy dx equals whatever. Okay? So this shouldn't bother us too much. Let's see what they want. Let y equal f of x be the particular solution. So here we go. We've got another terminology, the particular solution. And here is the initial condition. So basically, we have a point and we have a formula to help us find the slope. Okay? A little bit confusing, but I think we'll be okay. So in this case, we want the equation of the tangent line at the point 2, 0. So we have a point, but we need a slope. So in calculus, in order to find the slope, it's just the derivative. And we're going to evaluate that at the point 2, 0. So it's e to the 0 times 2 times 2 squared minus 5 times 2. And if you multiply that out, you get a negative 2. So we come up with a negative 2. It's that easy. So what we did is we gave you the equation to find the slope of the tangent line anywhere. That's the derivative. Okay? So let's go ahead and fill this in. Y minus the y value equals the slope, x minus the x value. And so we get y equals negative 2x plus 4. Now we're going to use this as to approximate values close to x equal to negative 2. Okay? I mean, x equal to 2. Sorry. The slope was negative 2, but our x value is 2. Are we close to 2? 2.2 is close to 2. So it's a good thing to use our tangent line to approximate that value. Okay? So let's go ahead and do that. F of 2.2 is about equal to negative 2 times 2.2 plus 4. If you work that out, it's negative 0.4. And that concludes this topic.